Let's have a look at this word problem. Actually, this word problem here is a demonstration of Pascal's law. So before we go ahead and solve the problem, let's have a look at Pascal's law. And here he is, Blaise Pascal. And what does Blaise Pascal have to say? Pascal's law. Oh, before we go ahead, have a look at this statement right here. It's interesting. But anyways, moving on to Pascal's law, it says here, his studies in this area led him to develop Pascal's principle or law. Oftentimes you will see this written as Pascal's principle, and the other half of the times you'll see it written as Pascal's law. I prefer to use Pascal's law simply because if you were to build a system based on his statement here, it works every time. And that is the basis of a law, just like the law of gravity. If I drop this pen, it will always fall down. Hence, if I build this system, it will always work according to what is written here. Hence, I prefer to call this Pascal's law. Still, let's have a look at what it says, Pascal's law, which states that a pressure applied to a liquid in an enclosed space distributes equally in all directions. Let me reread that. Which states that a pressure applied to a liquid in an enclosed space distributes equally in all directions. And we're going to do a demonstration of this via the word problem that we have. Let's have a look. So here's the word problem, demonstration of Pascal's law. It says here, a force of 55 newtons is applied to the small piston of a hydraulic jack. This here being a picture of a hydraulic jack, and here is the small piston. And this piston has a diameter of 20 millimeters. And in this hydraulic jack, there's also a large piston on the other side. Here it is. And it has a diameter of 150 millimeters. And if I were to apply a force here, that would develop a pressure inside this cylinder, because it's filled with a fluid, typically hydraulic oil. And that small pressure that I apply here will be a large output pressure, or I should say force. The small force that I will apply here would result in a large upward force here in the large piston. Let's have a look at this in the cutout. And here it is. This is the fluid inside. Here is the small piston. And here's this plunger that I can apply a force to. And when I apply a force to this plunger, a pressure is developed within this fluid, this typically being hydraulic oil. And this pressure that is developed here, as a result of my pushing down on this piston, that pressure is distributed evenly throughout this entire fluid. That is the basis of Pascal's law. The pressure developed here is the same and distributed evenly throughout, instantaneously, throughout this entire system. And here is the larger piston. In order for us to solve our problem, we're going to simplify this a little bit because there is a slight height between this piston and that one. And this height right here has to be taken into consideration, but that just complicates our word problem. So in order to make our word problems a little simpler, we're just going to make these the same height. Bring this one down, bring that one up so that everything's at the same height, the two pistons. So it looks like this. This will be the configuration that we are going to work with. Here is the small piston, here's the large piston with the fluid inside, and they're at the same level. That way I don't have to add the additional mathematical term for this height. So let's have a look at the word problem itself now. Here it is. A force of 55 newtons is applied to the small piston of a hydraulic jack that has a diameter of 20 millimeters. That is, the small piston has a diameter of 20 millimeters. If the large piston has a diameter of 150 millimeters, find A, the output force. I'm only going to find A for this particular video. I will leave this in postings. So let's have a look now. Let's draw this diagram. Drawing the hydraulic jack, we have a small piston, and it says diameter. That has a diameter of 20 millimeters. When you see diameter, we're talking circle. Yeah, let's wait for the focus to come back. Here we go. So it's circular in shape, small, and it's going to be at the same level with the large piston. And the large one also has a diameter, so it too is circular in shape. And it's going to be enclosed in a case. Something like this, just like you saw in the prior picture. And this is a piston right here. We're going to give it a seal. So everything here is sealed. So all the fluid that's in here, typically that fluid is oil. And this is sealed also. And I'll make the casing go a little bit higher. That way this piston can go up and down the walls of this casing without it losing any fluid. Because it has to be a contained system. Having said that, let's look at what else we have here. It says that the diameter of the small piston here is 20 millimeters, and the diameter of this one is 150 millimeters. And there's a force of 55 newtons being applied here. So let's draw that. And we'll call this side 1. So force 1 is 55 newtons being pushed down. That is the applied force. And then there's going to be a much larger force, an output force here, and we'll call this side 2. So we'll call this F2. We don't know the force output. We don't know. That's what we're looking for. Find the output force. Let's make a list of what else we have given, or what is given. Here we go, given. And we're given the diameter of the small piston. It is 20 millimeters. We'll call that D1 is equal to 20 millimeters. Now we already know that 20 millimeters is the wrong units. We need to change this to base units. So we divide this by 1,000 and to change it into meters, and that becomes 0.02 meters. And F1, the force being applied on the left side, is equal to 55 newtons. The output force, F2, well, we don't know what that is. And we're given a diameter. And we'll call this diameter 2. And that has a value of 150 millimeters. Again, we're going to divide that by 1,000 to change it to meters, and that is 0.15 meters. Now let's have a look at Pascal's law itself. If I were to apply a force here over this area, a pressure is going to be developed here in the fluid. Let's have a look at our equations. Pressure in a fluid is equal to the force applied divided by the cross-sectional area. We have a force. This is the area. Therefore, our pressure is going to be generated here as a result of this force over this area, according to this equation. And we'll write that over here. Pressure at 1 is equal to force at 1 divided by area 1. That is the pressure being developed here as a result of that 55 Newton force into the fluid. And let's apply this equation over to this side. Same principle. Pressure is force divided by area, except now we're going to use subscripts 2 here at this portion. So over here on this side, we have pressure at 2 is equal to force at 2 divided by area of 2. And here we have pressure at 2 theoretically using F2 and A2, this diameter or this area. Now Pascal's law states that the pressure developed here, this is where the action is, the pressure developed here is going to be transmitted undiminished throughout this system. So it'll be pressure at 1 will be here. Pressure at 1 will also be here, and it will go in all directions. That pressure being in the fluid will be exerted in all directions, on the walls here, on the walls here. All of it will be P1 right up to here. Well, we can calculate P2 based on F2 and A2, but P2 is going to have to be equal to P1, the pressure here. This pressure has to be equal to this pressure. Mathematically, pressure at 1 has to equal P2. Since these two are equal, then that P1 and P2 here are equal, then the right-hand sides must also be equal at this point and throughout the system. Therefore, F1 over A1 is equal to F2 divided by A2. This is Pascal's law in mathematical form. The pressure applied here, or generated here as a result of the force over this area, going to develop a pressure, and that pressure is transmitted throughout that system undiminished, such that the pressure going up here will all be P1. And we can calculate the pressure being developed here also using F2, if we knew what F2 was. Over this area would develop a pressure of F2, or P2 I should say, and P2 and P1 have to be equal because all of this has one pressure at 1. And it's described by this formula known as Pascal's law. Looking at what we have given, we have diameters, and we have the two forces, but what we need is areas, these areas. Well, we have diameters, so finding the area of 1, know the equation of a circle for the area is pi r squared. And this can also be written as pi d squared divided by 4. Since we're given diameters, we'll call this d1. I prefer to use this equation. And putting in the numbers then, it becomes pi times the diameter given to us in meters, squared divided by 4, and it'll be meter squared. And area 2, similarly, is equal to pi times d2 divided by 4. Putting in the numbers, pi times d2 was 0.150, 1.5 squared. Everything divided by 4, and the units will be meter squared. We now have everything that we need in order to fulfill this equation. We're searching for F2, so we can rearrange this equation. You don't have to do it this way that I'm going to show you right now. You can easily start solving these and just plugging in the numbers and algebraically solve for F2. I'm going to take a slightly different route. I'm going to rearrange this to isolate F2. Leaving F2 where it is, multiply the opposite side here times A2. A2 times F1 divided by A1. And just flipping this such that F2 is on the left-hand side. Force at 2 is equal to A2 F1 divided by A1. That's what I want to find. All of these I have, all these numbers, so it's just a matter of plugging in the numbers. So I'm going to do that next. F2 is equal to area 2. Without actually doing the mathematics, area 2 is represented by this term. Again, you don't have to do it this way. You can actually do the calculations and put in the numbers. Times the force at 1, which was 55 newtons. Everything divided by area 1, and that was given here. Looking at the units, meter squared and meter squared cancel out. This is just one large division sign right here. And the 4 and the 4s will also cancel out, and the pi's and the pi's will also cancel out. So this can easily be reduced to 0.15 squared times 55, and the only unit left over is the Newton, divided by 0.02 squared. Now putting this in the calculator, the answer is 3093.75 newtons. Per proper sig figs, go back to your original question, and we have three significant figures, and this was to be three significant figures with a little decimal point here. So we'll round this to 3. 1, 2, 1, 2, 3, and that's less than 5, so we'll go with 300 or 3090 newtons. Therefore, the output force here is 3090 newtons. All forces have the unit of a newton. Notice what happens. We have an input force of 55 newtons and an output force of 3090 newtons. And that is because of the two different diameters. If these were the same diameters, then the input force would equal the output force. But because we have a larger diameter here, the output force is going to be much, much greater. And all of this based on Pascal's principle or Pascal's law through here, through this fluid. And this has to be an enclosed system, which simply means no leaks. If this had a leak and water, if fluid and oil was leaking out, then this wouldn't exactly work. And this system is used billions of times a day, billions and billions of times a day. Billions of times a day. How do I know this? Because this system is exactly how the brakes work in a car. Here's where you will put your foot on the brake pedal, and your brake pedal is attached to tubes, which eventually lead to the wheels. And this is where the braking action occurs at the wheels. It doesn't look like this, but this is the principle right here that is being used, this hydraulic principle here based on Pascal's law. And it is immediate. As soon as you put your foot on the brake here, it is felt at the wheels immediately. And then this pressure that is developed here is transmitted across, from here all the way across, undiminished. So whatever pressure is developed here is equal to the pressure that is pushed on here, pushing the piston up. And because of its diameter, it is increasing the force considerably. That's how our brakes work. If your brakes happen to have a leak and fluid is coming out here because of some rust or something, and you go and step on the brake, well, the brake would simply, your brake pedal will simply go down as the fluid gets pushed out. In that scenario, then Pascal's system or law does not work. It only works in an enclosed system. So let's look at definition again. Pascal's law, which states that pressure applied to a liquid in an enclosed space distributes equally in all directions. The pressure is distributed equally in all directions.